Welcome to Tollefson Physics. So what we're going to talk about today are calculations that may be associated with the fan car project that our freshmen are doing. And so we're going to be making position and time measurements in the hallway, and we're going to be able to try to figure out what the accelerations are, figure out what the potential forces are on the car. So in this particular case, I have a 150 gram fan car that starts at rest and travels 12 meters in 4 seconds. The force of the fan is known to be 0.25 newtons, and so we're going to draw a complete quantitative free body diagram or force diagram for that car. We can actually start some of that diagram right now, right? So what we're going to have, I'll start it over here. So we're going to have a force due to gravity of the earth on the car, and since it's a 150 gram car, we're going to use 10 as the gravitational field newtons per kilogram on the earth. So that gives us a force due to gravity of 1.5 newtons. And then since it's on the floor and it's not accelerating in that direction, we have a normal force, and that's got to be the same size. The data that we collected tells us the force of the fan is 0.25 newtons. And presumably we've got some sort of friction / drag forces that are acting on the car. And so we're going to use that information. We're going to use our FNet information to be able to figure out what's going on. All right. So now let's go ahead. We're going to use this data. And so this data, I'm going to draw a velocity time graph for this. And so I'm starting at a rest, and in 4 seconds, I travel 12 meters. All right. So to be able to figure out what the net force is, I'm going to have to use Newton's second law, F net equals ma. Right? So I know the mass, but I don't know the acceleration. So I need to figure out the acceleration here. Now I'm going to start with an area equation because I know the distance. Right? So when I'm trying to calculate what the height of this is, that's going to be useful because, generally speaking, area is displacement. For a triangle, the shape is 1/2 base times height, which is time times velocity. So now what I can do is I can substitute numbers in for that, but I think what I'm going to do first is I'm going to solve for v, which I've done before. How do I solve for v? I multiply both sides by 2 and I divide both sides by t. And so what I end up with is 2 times x, and I'm dropping the delta because it starts at position equals 0, and divide that by t. All right, very good. So what I have is 2 times 12 meters, and it took 4 seconds. So you can do your math however you want. So 12 times 2 is 24, divided by 4 is 6. So my final velocity in this particular case is 6 meters per second. But that's not what I want to know for Newton's second law over here. I need the acceleration. Well, the acceleration is the slope, right? So acceleration is the rise, which is change in velocity, divided by the run, which is the change in time. So in this particular case, I have 6 meters per second for the velocity, and the time is 4 seconds. And so that is 1.5 meters per second squared. So now that's going to allow me to solve for the net force. Now remember, the net force is not a single arrow on my force diagram. It's basically the addition, the vector addition of all those arrows. But in this particular case, since the up arrow and the down arrow are equal to each other, they cancel each other out. And we only need to consider, well, I have this force of the fan to the right of 0.25, and then I have this backwards force of friction, let's call it, force of drag, that's going to make that net force less than the force of the fan. So let's find out what it is, right? So F net equals, now remember that Newton's has embedded in it kilograms, meters, and seconds. So I have to change my 150 grams to 0.15 kilograms. Right? Because really, what does this mean? This means 0.15 times 1,000 grams, which gives me back 150 grams. K is just the number 1,000. And then my acceleration's over here. It's 1.5 meters per second squared. And then this one will require a quick calculation. 1.5 times 0.15 equals, so the net force is 0.225 newtons. All right, that's a 2. So we have a forward force of 0.25. Basically, you can think of the net force as the difference between this right arrow and the left arrow. A way to write that mathematically is, in the direction of acceleration, I have the force of the fan. In the other direction, let's go ahead and call it force of friction. It includes some drag forces and stuff like that, but we really don't need to worry about that. We're just looking at the magnitude of that backwards arrow. And so, well, what is the force of the fan? It's 0.25 newtons. So how do I subtract, how much do I subtract to get 0.225? Well, it's 0.025, right? So minus 0.025 gives me 0.225. And so that is actually what the force, I'll just kind of write it up here, not the best spot, but I'll write it right there. So that is what that, based upon this data, right? So the data that we collected that says, okay, this car took 4 seconds to travel 12 meters, we're assuming a constant acceleration. And based upon that, then the net force is 0.225 newtons. But that number reflects this minus this. And so that's why we don't see that number, 0.225 newtons, on the force diagram. We see it in the math. All right, so let's take this one step further, and we're going to assume, let's do best case scenario prediction. So we're going to make a prediction instead now. So what if I could get rid of all the force of friction? What if I could do all that? So if I could do that and basically make the net force equal to the force of the fan, which is 0.25 newtons, what is the maximum acceleration I could get on the car? What's the maximum speed I could get on the car? So let's try to figure that out, right? So we're going to be able to calculate the acceleration using Newton's second law. And a common way to write Newton's second law is actually this way, where the acceleration is the net force divided by the mass. And so we can predict what a maximum acceleration is simply by saying, okay, let's set the net force to the force of the fan. All the friction forces are gone. And the mass of the car is still 150 grams, which is 0.15 kilograms. And so if I take 0.25 divided by 0.15, I get 1.67 meters per second squared. All right, so that's the maximum acceleration. But then I asked another question. I'm like, well, then how fast could this car actually go? And that just brings us back to a velocity time graph, right? Velocity time graph speeding up. The slope of this line is 1.67 meters per second squared. And then one thing this doesn't say, it was on the other slide. How far did it go on the other slide? It went 12 meters. So let's use that as our distance. And so we want to predict how fast that is. What's that speed? Along the way, we will discover how long it took to get there too, right? What would the stopwatch read when you do that? So once again, this is area and slope. I'm going to start, doesn't matter which one, let's start with area this time. And so the area is 12 meters. I'm going to substitute right away. And that equals the shape of a triangle, which is 1/2 the base times the height. So I have two variables I don't know, just like before. And then when I look at the slope, 1.67 meters per second squared, and that is rise over run, which is velocity divided by time. And then like what I typically will do is cross multiply 1.67 meters per second squared times time, and then that can go into that equation there. And so once I do that, then this looks like one of the kinematic equations that you would find in a typical physics textbook, x equals 1/2 at squared. That is the form that this ends up taking. So there's my x, there's my 1/2. And that's where the 1/2 comes from, at least from this kind of analysis. It's the shape of this triangle, assuming a constant acceleration. The velocity is 1.67 meters per second squared. That's actually the acceleration, but I'm substituting in this term for velocity, which is times t, and then there already was a t, so it's t squared. So what I need to do is I need to combine these. So 12 times 2 is 24. 24 divided by that gives us a time squared of 14.4 seconds squared. All right, and so then what's the actual time? We got to take the square root of that, so put that to the square root there, and I get 3.79 seconds. All right, if we compare what we had before, when we had the friction forces present, it took 4 seconds. So it should make sense. It should make sense that it took less time because it's accelerating at a greater rate. So it takes less time. So it's always good to sit back and look at your results and say, oh, does that actually make sense? So in this particular case, it makes sense. But this doesn't answer the question. The question that I asked was, what is that maximum possible speed that it could go? And so we'll bring down this equation again, 1.67 meters per second squared times 3.79 seconds. And so that final velocity, grab Mr. Calculator here, times 1.67 is 6.34. 6.34 meters per second, which should be faster than it was before. And is it? So before we found out that it was 6. So yeah, good. Higher acceleration leads to a higher velocity. All right, so using Newton's second law, we're able to tie together some observations that we make on our fan cars and be able to make some predictions about maybe some of the forces that are a little harder to measure and try to understand how our cars are moving using Newton's second law. Now I want you to try this problem here. So now instead I have a rocket car, has a bit higher acceleration, higher force on it. So it's a 250 gram car because it's holding a rocket booster, so it's a little heavier. It travels 10 meters in only 2 seconds when starting from rest. So I actually want you to determine a couple things about this. So first, I want you, using the experimental data, determine what the acceleration and the maximum speed of the car was. Then, knowing that the force of the propellant of the rocket is 3 newtons, I want you to draw a free body diagram or force diagram for the car that reflects that using the net force. Pause the video now and give that a try. Alright, so now let's take a look at this. So I'm not going to draw a little picture this time because I'm going to run out of space, but I will draw my velocity time graph because it's still super duper useful. I have this car that's going to speed up. We're going to assume at a uniform rate, which may or may not be true, but we're going to go there anyway. And it took, what, only 2 seconds to go 10 meters. So that's screaming out, let's use area to try to solve what's going on here. So once again, the area is known as the displacement, and 1/2, it's a triangle, so it's 1/2, base is time, height is velocity. So let's go ahead and I'll directly substitute the numbers in this time. So 1/2 times 2 seconds times v. So the 2's cancel each other, so that final velocity ends up being 10 meters per second. All right, so it's cruising. So now let's go ahead and figure out the acceleration. So the acceleration is based upon the slope. So the slope is known as the acceleration, which is that change in velocity divided by change in time. So in this particular case, that change in velocity is 10 meters per second, and that change in time is just 2 seconds. So 10 divided by 2 gives you 5 meters per second squared. Now, one thing I didn't ask, but it's going to be necessary for the next part of the question, is we need to figure out, okay, what's the net force on the car based upon that? And so the net force, let me write it here, F net equals ma. And so the net force is going to equal the mass of the car, and we have to do that in kilograms. So 250 grams divided by 1,000 gives us 0.25 kilograms. We're going to multiply that by the acceleration, and so 0.25 times 5 gives us a net force of 1.25 newtons. All right, so actually that force probably should have been 2 instead of 3, but let's go ahead and draw a force diagram based upon what I was given to you. Let's use red for that. So force diagram is going to look something like this. So we're going to have a force due to gravity of 2.5 newtons. We're using little g equals 10 newtons per kilogram in this case. So it's a quarter of a kilogram. Multiplied by 10, you get 0.25. The normal force will be the same because the forces in those directions are balanced. It's not accelerating. Now the problem gave you a force of the propellant. I'm just going to write it F. Of 3 newtons, which is actually a bit high given this value here, but that's okay. And so the net force is the difference between the two arrows. So I have whatever these drag forces are. Let's just call it force of friction. Let's also say it's speeding up so much there's a lot of air resistance. We'll just call all that resistance force of friction for now because we don't have a way to separate them. And so basically this is saying, oh, that force going forward minus the force of friction going backward, slide that over, is equal to 1.25. Well, this force is 3 newtons. And so this backwards force, like I said, is a bit high for this. But if I take 3 minus 1.75, I get 1.25. All right, so just remember the net force is essentially you're adding up all the arrows. You establish a coordinate system. So to the right in my case was positive, to the left was negative, and so 3 minus 1.75 gives me a net force of 1.25. All right, keep practicing these problems and you will improve. Good luck to you.